So let's continue talking about the properties of electrons in metals. We will now consider AC electrical conduction in metals. We have talked about DC electrical conduction, we have talked about the Hall effect. We will now talk about AC electrical conduction. So we will assume that the metal is subject to an electric field which is oscillating of this form. This is the form used by Ashcroft. The usual form that is normally written in textbooks has got E naught as the amplitude, but this just means that this is also the amplitude, but this means that this is the amplitude for that frequency omega. That's all. So there's not a big difference between the two. So we will continue to use the Ashcroft form so that it's easy for you to track with the textbook. Now this is the equation of motion we derived, and we will use that and again here, and so this E will just be represented by this oscillating form. So immediately you can recognize that because the electric field is oscillating in nature, the momentum of the electrons will also become oscillating in nature and will also take up this form. So if I stick these two expressions inside, I can write down this kind of an equation, and the current density J is related to the momentum, and therefore the current density J will also have an oscillatory form given by this, and because of this expression I can now write J of omega in terms of a P of omega, and I can now use this and put this inside, and I should be able to write this expression. So again, I'm not going to derive every step. You will have to pause the video and calculate it for yourself and see. That's the only way to learn. Whether it is done on the blackboard or on a video, it doesn't matter. You will have to pause and take the time and write down on your notebooks and learn. I will not be saying this again and again throughout the course. You will have to do it, otherwise your learning will severely suffer. So now I can write this expression for J of omega in terms of E of omega like this. So now I have a frequency dependent conductivity. Earlier we had J equal to sigma E as the form of Ohm's law, and that's for DC currents, but for AC currents this can be thought of as the equivalent of Ohm's law, and a sigma of omega is this nice little expression over here, and sigma naught is basically the DC electrical conductivity, which is Ne squared tau by m. Now there are a couple of approximations here. In this discussion we do not consider the magnetic field, that the effect of the magnetic field applied on the metal. This is because the ratio of the E field to the B field is equal to the speed of light, and therefore the electric field is significantly stronger than the magnetic field. The impact of the electric field is significantly stronger than the magnetic field, and therefore in the case of oscillating electromagnetic fields, typically the electric field will be the dominant contribution, and therefore we consider that only. And also we don't worry too much about the spatial variation in the amplitudes of the electric field. We shall assume that we are working at room temperature, and we are working with visible light, so that visible light will have wavelengths of like thousands of angstroms, and at room temperature the mean free path is only about 1 to 10 angstroms. So we are working in a region or a regime where the lambda of the electromagnetic light is much greater than the mean free path, so we don't need to look at the spatial variations within the metal. We don't need to worry about the spatial variations. Now we use the standard set of Maxwell's equations, and we will derive the wave equation from this, and for this kind of an oscillatory electric field, and then we will end up getting this form of the wave equation. And please recall here this J is basically sigma E, so that's where the sigma comes in. In this expression for the del cross B, you have the current density J, and that is equated to sigma E, and that's where the sigma comes into play. So you can insert this, do the standard math for the wave equation, and you will be able to derive this form for the wave equation. And this can now be written as this term within brackets can be written as a frequency dependent dielectric constant, which is given by this. Now, given this expression for, now we have an expression for the frequency dependence of the conductivity and the frequency dependence of the dielectric constant. Now, if you assume that we are working in the regime omega tau is much greater than 1, that is at very high frequencies, then this I can approximate this, I can introduce this expression for sigma into this dielectric constant equation. So there's a sigma here, I can replace the sigma by this expression, and I can approximate this epsilon of omega as this form, where omega p is given by this. That's called the plasma frequency. So I can now write the epsilon of omega in the limit omega tau is much greater than 1 as 1 minus omega p squared by omega squared. Why this is called the plasma frequency and the significance of that is what we're going to see now. Now, to understand the significance of the plasma frequency, if I now express the electromagnetic wave as a spatially oscillating expression given by this E naught e power ikx, then I can rewrite the same wave equation in a slightly different way. I can write this prefactor for the electric field omega squared by c squared epsilon of omega as a wave number. So I can write this as k squared, and given this expression for epsilon of omega, if omega is less than omega p, so if you apply an electromagnetic wave to the metal with a frequency less than the plasma frequency, the dielectric constant because of this would be real and negative. The dielectric constant would be negative. That means that because of this expression here, k would be imaginary. So this means that the wave will decay exponentially inside the metal. So for any frequency which is less than the plasma frequency, very little of the wave will go inside the metal, much of it will get reflected out. That's why the metals are considered shiny for all frequencies less than the plasma frequency. But if you apply a frequency greater than the plasma frequency, then epsilon of omega will be real and positive. So as I increase the frequency from omega less than omega p and to move it to omega greater than omega p, the dielectric constant goes from negative to positive. So there is a zero of the dielectric constant at omega equal to omega p. So for frequencies greater than the plasma frequency, the dielectric constant is real and positive, and therefore the wave number is now real, which means that the wave actually propagates without decay and the metal becomes transparent. So the metal becomes transparent for frequencies greater than the plasma frequency. And the reason why it is called the plasma frequency is because for frequencies greater than that, what happens is the entire wave goes through, and because of that, now you have a collection of free electrons, and you are applying an oscillating electric field. So when the electric field is in one direction, the electrons are polarized in one direction, and when the electric field oscillates in the opposite direction, the electrons are polarized in the other direction, and back and forth. This creates a kind of a charge density wave in the solid, and that's why it's called the plasma. You can think of this electron gas as a plasma which is oscillating back and forth, and that's why it's called the plasma frequency. So these are this is again a table from Ashcroft. These are the observed and the theoretical values of the wavelengths below which the alkali metals becomes transparent. So for alkali metals, there's a reasonable match between the experimentally observed value below the frequency below which they become transparent and the theoretically obtained value from the simple Drude model. There's a reasonable match. For other metals, there is not much of a match. We have to use other methods, but at least for the alkali metals, there is a reasonable correspondence. So we will now look at this plasma oscillation. It's also called a charge density wave or a plasmon. Because the electromagnetic waves can propagate through, we now think of the charge density as oscillating and having an expression of this form. This is called a charge density wave. And please recognize this rho here in this context is the charge density. It is not the resistivity. Depending on the context, we have to use the symbols appropriately. You cannot be saying again and again what is it every time. So this is just the charge density here. So if I now combine the equation of continuity, which is given by this, and the simple Gauss's law, which is given by that, and if I use this, the frequency dependent form of the Ohm's law, if I combine all of them together and use this expression, I should be able to derive this condition which connects the conductivity and the frequency dependent charge density. And you can immediately see that the expression within the bracket is just epsilon of omega. So you can't have rho of omega going to 0. So the condition for the propagation of a charge density wave in a metal basically corresponds to the condition where the frequency dependent dielectric constant becomes 0. So that is exactly the condition where when omega is equal to omega p. That is, we just saw that before. When omega is equal to omega p, that's when the propagation of charge density starts. For all other frequencies from omega p and above, for all other frequencies, there can be a propagation of a charge density wave because of the polarization caused by the oscillating electric field, which travels unhindered through the metal. Now, you can write a very simple equation of motion for this oscillating plasmon of the plasma or the oscillating electron gas by simply writing mx double dot is equal to minus the electronic charge E times the electric field capital E. That's just the standard equation of forces, and with that you can write write down the simple expression, and this essentially means that the frequency of oscillation is just the plasma frequency. And I would suggest, if you're interested in plasmon resonances, plasma frequencies and so on, you can search on YouTube. There's one particular simple video called Surface Plasmon Resonance Explained. So the way you detect this is you basically coat a metal on a glass wafer or any other substrate. Then you basically have a two-dimensional form of the metal. You have a thin film of the metal, and if you reflect light from this metal at a particular frequency and a particular angle of incidence, there will be absorption. The material will absorb the light, and basically the light, almost the entire light will go through the film. That's because the plasmons are getting excited, and you're basically creating a plasmon resonance at that particular frequency and a particular incident angle. That's called surface plasmon resonance. There are many applications to this because it's heavily dependent on the substrate, the nature of the substrate, the dielectric interface, and so on. You can see further, you read further about it if you're interested. So now we will look at the last part of the Drude model, which is thermal conduction. So in thermal conduction, basically what happens is that you are heating one end of the metal, and the other end is at a lesser temperature. So there is a thermal gradient and there is a thermal current that flows. Now the thermal current that flows will be opposite to the direction of the thermal gradient. So to express this, the thermal current JQ, that Q is for heat, the thermal current JQ is written as minus K delta T. That K is the thermal conductivity. The thermal conductivity is always defined to be positive, and that negative sign is basically to ensure that the JQ is basically in the direction of heat flow. The JQ is represents the direction of heat flow. To get the direction right, you put the negative sign in. That is because if I take one dimensions, and we are only going to stick to one dimension. If I have T1 temperature at one end and T2 temperature at other end, with the T2 greater than T1, so this is the positive x-axis here, and the slope dt by dx will be positive. But the heat will flow the opposite direction of the gradient, because this is at a higher temperature. So heat will flow from higher temperature to lower temperature. To represent that, you write the negative sign is put there, and this is called the Fourier's law. So we will stick to a very simple one-dimensional model to understand thermal conduction. And we are also going to assume that if all the heat is transported by the electrons alone and the lattice does not, that is the cores, the core electrons plus the nucleus, they don't get involved in the heat conduction. That's not a correct assumption to make, but for the moment we'll stick to it. At least for metals, to some extent, at least at high temperatures, it should be a reasonable assumption. Now, one of the basic approximations of the Drude model was, we said that the energy of the electron depends on the temperature of the place where it had the last collision. If the temperature of where the electron had the last collision was high, then the velocity of the electron will be high and the energy of the electron will be high. That's the general idea that we used. Now, what we are going to assume here is that in addition, that there is only heat conduction. There is no electrical conduction. That is, the average electronic velocity at any point in the metal is 0. That is, you have equal current of electrons flowing from right to left and from left to right. So there is no electrical conduction, but there is heat conduction. That is, these electrons, that is, the electrons flowing from the hotter end to the colder end will have more energy compared to the electrons flowing from the colder end to the hotter end. Because of that, there is a net transfer of energy. There is a net thermal transfer, but there is no electrical conduction or charge transfer. There is a reason why there is no charge transfer. We will talk about that after we finish the thermal conductivity discussion. So we are going to assume that the average electronic velocity is 0 at any point, and that's a reasonable approximation to make. So if I consider the the energy of a single electron as E of t, then that expression means that it is dependent, the energy depends on the temperature at the point x. So if we have electrons going from left to right, and we will represent that as E of t of x minus vt, where v is the velocity and tau is the relaxation time, because that's the after a single in between collisions, that's the kind of velocities that's the kind of energies that the electrons will have. The thermal current will be half the number of electrons per unit volume, n by 2, into their velocity into this energy. And for electrons going from right to left, you will have E of t plus t of x plus vt, because of the signs. We have taken a one-dimensional model, and this is the positive x direction. So you will have right to left will be here, and left to right will be that side. So right to left will be having x plus vt, and the thermal current will be n by 2 into minus v, because the direction is opposite to the or the direction is along the negative x-axis. That's why it's a minus v, and again it's E of t of x plus vt. So I can now write the thermal current as a sum of these two contributions, and we are going to make an expansion of this term with respect to x. But to simplify matters, I will remove the t for now, and I'll just write it as the energy of x minus vt and energy of x plus vt, and we will put back the t later on. So this is a simpler way to look at it. Then I do a simple Taylor expansion for both these terms, and that's what I'll get. And if I simplify, I'll get this expression, and I now have dE by dx, but I can now replace this as dE by dt into dt by dx, and that brings back the thermal gradient into the expression. So the thermal gradient is necessary, because otherwise we can't calculate, because this dE by dx is something I cannot calculate in an experiment. So I replace that by this product. So given this, I want to go over to the three-dimensional case. So obviously the dt by dx will become a gradient in 3 dimensions. This v squared, I will write this as this is just the average velocity, vx squared. So in one dimensions, but that's equal to the three-dimensional velocity v squared by 3. It's 1/3 of the three-dimensional velocity. So I will write this. I will still, I mean, this was a one-dimensional model. I don't need to worry about x or y axis in this case. But now I will replace this. I will explicitly say it is along the x-axis and go to the three-dimensional case. And there the vx squared will now be, I will have vx squared instead of v squared. And this vx squared, I can write it in terms of the full velocity v squared by 3. Of course, is the average. So, and also I have this term n dE by dt. Now this n is equal to the total number of electrons divided by the volume, and this is dE by dt. So this n into small e will be the total energy. I can write this as dE by dt per unit volume. This is essentially the definition of specific heat. The specific heat is the rate of change of internal energy per unit volume. This internal energy is basically the total energy of the system. So the specific heat is defined as the rate of change of internal energy with respect to temperature per unit volume, and that's a definition. You will learn more about how this definition makes sense and what you can do with it and so on in the parallel course statistical physics. So I now make those changes, and I now have this for thermal current. And remember the Fourier's law, which we wrote as JQ is minus K gradient of T. And now I have now I have an expression for the thermal conductivity, which is given by this. So I have this can be written in terms of the mean free path. We have a v squared tau, and I can write this as L into velocity. So it's 1/3 LV into CV. Now at that time when Drude proposed this, there was no quantum statistics available. People did not know anything about quantum mechanics much, and so Drude used the classical expression for specific heat, and that is derived from what is known as the equipartition theorem. So the equipartition theorem says, so suppose I have a free particle, then it will have the free particle will have let's say it can move in 3 dimensions, right? So every dimension will contribute half mv squared to the kinetic energy. So for every degree of freedom, the equipartition theorem says the contribution to the average energy is half kT. Now this is a result I am just stating. Some of you may have studied it in school, or the BSc students must have studied it there. The MSc students must have studied it in BSc. But if you have not come across this, don't worry. This is one of the first things you will be deriving in your statistical physics course. I don't want to do it again here. So for a free particle, the equipartition theorem simply states that each degree of freedom contributes half kT to the total energy. So you have the total energy per particle will be 3/2 kT, because there are 3 dimensions, right? It's 3/2 kT, and because of this, and I just said that the specific heat is basically the rate of change of the internal energy with respect to temperature. So if this is the internal energy, the specific heat will be the derivative with respect to temperature, which is just half kB. So each degree of freedom contributes half kB to the specific heat. There are 3 degrees of freedom. So it is 3/2 kB into the number of particles per unit volume. That's why you have 3/2 nkB. That's the expression that Drude used. Now what happened was a very happy accident. The classical expression for the electronic specific heat. So we have electrons, which are the guys which are conducting heat here. So the specific heat is basically the electronic specific heat. The electronic specific heat computed classically is 100 times higher than the experimentally observed value. I will explain why this is the case in the coming videos. So in this expression for the thermal conductivity, CV was overestimated by 100. But thankfully for Drude, and luckily, the classical average velocity V is underestimated by 100 times. So CV is an overestimate by 100 times. The velocity V is underestimated by 100 times. So if I take the product, they will cancel each other off. So let me say that again. The classical expression for the specific heat for electrons is a overestimate by 100, by a factor of 100. That is, if the experimentally observed value is only 1 unit, the classical expression says it's 100 units for the specific heat in appropriate units. So the classical value of CV is a overestimate by 100. The classical expression for the velocity is a underestimate by 100. So this overestimate into underestimate by the same amount cancels off, and that is why Drude was able to get a reasonable match for the thermal conductivity. It was a happy accident. Now we have the expression for conductivity, which we know we derived in the previous videos. So if I divide the thermal conductivity by the electrical conductivity, I will be able to get this expression. Please show this expression. Please show that's what you get. You have K here and you have sigma here, and you take the ratio, you will get this. And this is basically a constant times the temperature. So K by sigma is directly proportional to temperature, and the proportionality, there's a proportionality constant, and this is called the Wiedemann-Franz law. Now this Wiedemann-Franz law was experimentally, it was an empirical law given by because of experimental data, but Drude model was able to accidentally prove it. Like I said, it's an accident because specific heat is a classical specific heat is an overestimate by 100, by a factor of 100. Classical velocity is an underestimate by a factor of 100. They cancel off, and also if you notice this, there is a relaxation time tau here. There's a relaxation time tau in the sigma, but if I take K by sigma, the tau cancels off. So because of that, like I said in the previous video, if the relaxation time does not appear in the expression, then just by a stroke of luck, the wrong classical result matches with experimental, and that's what happened here. So now we will talk about the Seebeck effect, which is a consequence of thermal conduction in the next class.